So getting back to this structure, which is alpha-D-glucose 1-phosphate, the reason why I throw it out there to you is because of this inorganic ester functional group. But this compound is actually one of the first steps in making glycogen from glucose. So glucose at first has to be phosphorylated in order for it to then go on to become glycogen. And I quickly went over this, but it's you've heard of these terms ATP, ADP, AMP, which are basically energy units that we use in our body to run cells and do work. So when you have 3 phosphorylated compound, then it's the ATP, and then when you have 2 of them, that's ADP for diphosphate, and then when you only have 1 phosphate group, that's AMP. So and then the last thing is, what is the most important thioester in biological system? The answer to that is a thioester, actually not a normal ester. So that means it has a carbonyl, and then instead of an oxygen, you have a sulfur attached to it. And probably the most famous of this is acetyl-CoA. So it's got the CH3 here, and this is oftentimes abbreviated as acetyl-CoA coenzyme. And maybe you've had this before in biology classes, but acetyl-CoA is one of the important intermediate in Krebs cycle. So a lot of the you see the acetyl-CoA here is derived from all these amino acids and things like that, and then it enters the Krebs cycle, or the citric acid cycle, in this form. And if you want to take a look at this huge structure, this is what it looks like. Obviously you don't have to memorize or do anything like this. I just wanted to show to you what acetyl-CoA looks like. So here's the thiol group, the SH, and that's what is going to be in an ester functional group over here as a thioester, and that's a very important structure. All right, so the whole point of this is for you to realize how important ester functional group is in nature, everyday life, in your body, in metabolism, in everything. All right, or even man-made polyesters. You're using it, and you'll be looking at a lot of reactions. So if anything, esters and amides from this unit, you should definitely know backwards and forwards. All right. So then I'm going to move on to the reaction, naming and the reaction part of this ester. So naming esters is a little bit more trickier than naming acid chlorides or anhydrides. Okay. So when you have an R, C double O R, okay, that's the ester, what it looks like. You have two different R groups, and I think that's where the confusion comes as to which group is what. So once again, go back to the carboxylic acid, because all these are carboxylic acid, right? So the OR is really replacing the OH, right? So this part right here, you're going to name as a derivative of an acid, and this R prime here, that's attached to the oxygen. So the R prime attached to oxygen, that's not part of the acid. It's going to be named as a substituent. Okay, so if R prime was CH3 in this case, then it would be methyl. If it was 2 carbons long, it would be ethyl. So you name that as if it was a substituent, okay? And then you go back, cover this up, and you go back and look at what kind of carboxylic acid derivative it is. And then what you're going to do is name the acid derivative. By dropping the ic acid and replace it with 8. Sort of like how you name like sodium acetate, you know, that's the same model that you're using. Okay, so in naming this, all right, so what I recommend you do is you go to the R prime group, or the R group that the oxygen is, the R group that is attached to the oxygen. So what group is this? All right, name that as a substituent is isopropyl. And now cover that up so that you don't get confused. What acid are you looking at here? Is a benzoic acid, right? So benzoic acid, you're going to drop the ic acid and then replace with 8. So benzoic acid, I'm going to get rid of the ic acid and then replace it with 8. So then is benzoate. Isopropyl benzoate is the name of this ester. And then you should also be able to, given a name, draw the appropriate structure. So this right here is indicating to you that's an ester. So you know that ester has this kind of functional group. So go to here, because that's going to be your R prime that's attached to the oxygen. That is phenyl. And then 2-methylpropanoate. All right, so propanoate is the derived from propanoic acid, right? So this is carbon 1. That means it has total 3 carbons for the propanoic acid. So 1, 2, 3. And then on the second carbon, which is here, you have a methyl group. Okay, so notice it's a little complicated because you have a substituent off of the propanoic acid as well as a substituent on the oxygen. But the substituent on the oxygen comes always first in the name before the substituent for the carboxylic acid. So if you put in the right number of hydrogen on this, this is what this ester would look like. All right. Now, looking at how to prepare esters, probably the method that you've seen so far is the second method that's written here, which is from acid chloride or anhydride and an alcohol. So this is what you've seen with the acid chlorides and anhydrides. So here's a general reaction with an acid chloride. Sorry, this is not very dark. And you have the ester replacing, so or the alcohol replacing the Cl, and this would be the byproduct, right, HCl. So in order for us to make sure the HCl doesn't react with the product, we use pyridine. And in this specific example, we have C6H5, which is the phenyl group, and then you have the alcohol that is being reacted is ethanol, so you have an ethyl ester, and then the byproduct will be the pyridinium chloride that is produced as the byproduct, right? So you've seen this before, and that's one way to make esters. So that's from acid chloride, and then secondly is from anhydride. So we have R, C double N O, O, C double N O, R, and then if you react with an alcohol, you also get ester, as you've seen before, and the byproduct would be one of the carboxylic acid. So there's actually a mistake in this. There shouldn't be a 2 molecule of acid, just one is an ester and one would be an acid. So here's an example of acetic anhydride with benzyl alcohol. Then you would have this alcohol being added, benzyl ester of the acetic acid, and then the byproduct would be the acetic acid. All right, so that would be the ester that you form. All right, what you haven't seen is chemistry of the carboxylic acid. So preparation, which is the more common one. This is very easy way to do it in lab. So pretty much most of the time you will see this preparation rather than from acid chloride or anhydride, because a lot of times the acid and the alcohols are available in lab, and you just basically mix them together with acid catalyst, and you cook them and you get your product. Whereas acid chloride and anhydride, you either have to buy it or make it first and then react it. So this is, this would avoid that process, because you would directly react the acid, carboxylic acid, with an alcohol. All right. So the overall reaction is very simple. You take a carboxylic acid and you react it with some kind of alcohol, and you get an ester, and the byproduct is water. It's being extruded, and this is an equilibrium process, and you need an acid catalyst to make this reaction go. All right. So here's a mechanism of the reaction that I'm going to go over, which is something that you should be able to draw. So this is where I think your book does a really good job of looking at the overall what happens. So notice in this reaction we're doing under acidic conditions. So that means the intermediates that you propose are not going to be negatively charged, but probably positively charged in everything that you draw, as you will see. So you wouldn't be able to, for example, take an alcohol that's neutral and be able to directly attack the carbonyl of the carboxylic acid, all right, because that would make it O minus. So rather, because you have an acid catalyst, probably the first step is going to be the protonation of the acid, because this is going to be acid catalyst. Then you would have an oxygen with the plus charge, double bonded. Okay, everything else is exactly the same. So by protonating the carboxylic acid carbonyl group, you're making this carbon more electrophilic, more prone to attack, which then will be attacked by the whatever alcohol you're using. So this example is a methanol. So then that breaks open the double bonded O. And so this is where, to draw a bond between carbon and oxygen, right? That's where the bond is formed, right here, at this step, when the methanol attacks. So then you have OH, and everything is singly bonded. And then this oxygen would have a plus charge from the alcohol that it has attacked. And then what is going to happen is then the oxygen with the lone pair is going to come down and remove the water. But I guess I skipped a step here, and that is the proton transfer is going to have to occur. So this is going to have to grab this proton in order to form the water. So that's going to have the plus charge. The O minus is going to come down. I mean, the lone pair is going to come down and then kick out the water. So that's where the water is extruded. And you have this oxygen with the plus charge. So this extra proton is then deprotonated. And you have the ester functional group, as you see here. So the last step is regeneration of the acid catalyst. All right.